Hello, everybody. We are moving a little bit from the micro to the macro world. Mass wasting is one of the most significant geomorphological processes. These processes have not only been observed on Earth. You see here, we have them observed on comets. We have seen them on asteroids. And we have mapped them on the moon, as the two images on the right side shows. The cartoon on the left side should give you a little bit an impression how one tries to classify those mass wasting processes and those landslides. When I show you here an image which is only a couple of days old, I'm doing this because I'm showing you here at this lovely place in the middle of Switzerland, a huge landslide which is taking place and which has been monitored with all the technological possibilities which we have at hand. And despite this, we are unable to predict what's going on and get the timing precise. Within one night, this whole rock came down and nearly wiped out this image. And the projection and what we thought, were only approximation in terms of one had expected. Now, several teams and groups have tried to summarize what we have observed on the moon in terms of falls, rock slides, debris slides, lumps, flows, sweeping flows, creeps, and so on. So we have these type of maps, and as this former image showed you, it's a highly complex process. But the fantastic thing is here, the moon is not only for us an archive in terms of the history of the solar system, if you think of solar wind implantation, but it's also a fantastic lab to investigate some of these geomechanical processes. And I'm absolutely intrigued what I heard this morning in terms from our Norwegian colleagues and the research they are doing. Now, I'm only focusing on the absolute simplest case. I'm looking at the rock falls. So just boulders which roll and which leave a track. So why are we doing this? These type of rock falls, we are interested in finding out ultimately what triggers them. And there are internal and external factors. And here again, I only look at the external factors, namely the weathering of the rock strata and the earthquake and vibrations as a possible mechanism to trigger those faults. Now, there are two camps in the literature which very often discuss and you dispute what is really going to happen. And I want to explore with you a little bit what we actually can see. So I'm only looking here at the weathering processes. Everybody from you knows, without doing any computation, when you want to take a sun bath, where you put your chair, whether you're going on the north side or the south side. Now, if you look at the moon, it's a little bit more complicated. And I've produced for you here, you see it here on the top side of this panel. You see on the uppermost row, the same crater with an aspect angle of 0.2, so the diameter to depth ratio. In the middle, you see the same crater at the equator, and in the lower one, you see the same crater again at the southern hemisphere. And when I move now the illumination over the local hour angle, you see how we have a gradient going from north to south. At the equator, it's homogeneous. In the north, the northern part of the crater has obviously a higher temperature, on the lower, a smaller, and it's reverse on the southern side. Now, I have no time to go in all the details. This is the situation for the crater walls. Jamie Molaro and colleagues have worked out the details, what's happening to a boulder being sitting in the lunar regolith as the sun changes, and looked at the thermal conditions and the thermal stresses. And I recommend to you that if you are interested, you are reading these very interesting papers. So we have two situations. A rock could be sitting there, could experience a thermal shock, and could start falling because of the mass imbalances which develop, or it could stay there, and over time you would have a thermal cycling known as rock fatigue. If you go into the literature, you see the extreme cases from people arguing that there should be no thermal fracturing taking place, to the fact that we now have observed on Mars the thermal stress-induced rock falls on the crater slope. And if you go through recent literature, you find a lot of contradicting papers on this subject. We are clear. There are several factors. There are the environmental factors, there is the rocks themselves, and there is the stress loading, which can be different. And of course, the situation is complicated because you cannot investigate this separately. You are faced with the situation that all these factors play a role. Now, the first thing we wanted to do, we wanted to find those boulders. And thanks to LRO, we were able, in the framework of a PhD thesis, to produce a map of these rock falls. On the top image you see here from Kreslavsky and Jim Head, an investigation which shows you the slopes of these lunar topography. And you see there are only few places where you have these high slopes, mainly in craters. And so it's not a surprise that we find in this artificial intelligence search the boulders sitting in those craters. So we have generated an archive of 160,000 lunar boulders with tracks. And now the goal is, of course, to use this information. So the question is, can we really trust these artificial intelligence results? And in order to do this, I was hoping some colleagues would take up these archives and investigate it, but unfortunately nobody was willing to do this task. So I used the pandemic to do it with a colleague myself. And we have chosen something like 180 craters all over the moon, and we're with imaging and directly searching, looking for those boulders. We tried really to use exactly the same image database which the artificial intelligence had. So the problem you already see, what the artificial intelligence, you feed them all these images in, but you have this area which are shaded. You can work this out, and we have done this, and you can ultimately create, of course, nice mosaics without any boulders, without any shades, so that you should see really all the boulders. Here you see some of these boulders. So I just show you some results from the imaging approaches that we really see those types of tracks on these images. This is one of the results for one particular crater. You see on the right side what we have in the RE database and what we find. So instead of 98 artificial intelligence boulders, a human search with the help of imaging finds 1,200. And this is the summary which shows you that the RE actually only finds, 20% at best. So how can we now go and try to find out whether this thermal weathering is at work? The idea is we need an area of investigation. This should be clearly defined. The crater is an ideal thing. So all we need to do is focus on craters, but we need, of course, craters which are absolutely symmetric. We cannot use craters which I show you here, which have a structure, which have superimposition, which are all inside this artificial intelligence database. And once we have good craters, we simply can try to find this. So here I pick one particular crater where we have an image. I show you the elevation. I show you the slope angles. We are looking for the symmetry, asymmetry of the slope walls. And if I say this is a decent candidate for doing the research, I can start counting. Now, what we noticed that even for the human, sometimes it's very difficult on these images to spot all those boulders. And here comes the optical maturity information in place. We found a clear correlation between boulder distribution density and OMAT. And I just give you now an example for a non-symmetric crater. When you look directly on the OMAT map, it pops out that these boulders, which the artificial intelligence would count, you would realize that there are new craters in the crater itself, which are destroying your statistic. Here an image. So what we can now do is we can go and count, and I spare you here from going over 180 craters into the statistics, but you clearly see high latitude craters show the statistics that you have this northern south asymmetry. You have at the equator more or less an equal distribution, an asymmetry north-south, and you can then observe also the southern asymmetry. So I summarize. We have clearly shown that we find these asymmetries pretty consistently. We have shown that you cannot trust artificial intelligence just out of the box. You need to be very careful. And I also would like to stress that, of course, not all the craters which we see have this pattern. We have found some very interesting cases where we do not find these asymmetries. And this is not surprising because the world is not black and white, meaning we only have the thermal. We also could have, of course, the impacts which are triggering some of these boulder rockfalls. So let me thank once more Mark and his team for using this data. It's absolutely fantastic what we can do it. I would also mention Eric Mallory because the progress in the CRIPMAC site has been fantastic, and some of the stuff which we have done offline, you could even do today on this site. So I'm looking forward especially to talk to some of my colleagues here in terms of these geomechanical aspects, and I think there's a lot of fascinating stuff coming out. Thank you very much.